The universe, vast and infinite, stretches far beyond what our eyes can see or our minds can fathom. For centuries, humans have looked up at the stars, marveling at the beauty and the enormity of what lies beyond our planet. Ancient cultures wrote stories and built elaborate myths about the heavens, attempting to explain the cosmos through their limited understanding. Even today, as we have advanced in technology and scientific knowledge, we are still just beginning to understand the full scope of the universe. What we once thought were unmovable truths about space and time are now being called into question by new discoveries that reveal something far more complex and far more strange. For thousands of years, humans assumed the universe was a fixed, orderly place. Early astronomers, such as Aristotle and Ptolemy, believed that the Earth was at the center of the universe, and everything revolved around it. This geocentric view was the prevailing belief for centuries, supported by the Church and most of the scientific community. But as history marched on, new thinkers challenged these old assumptions. In the 16th century, Copernicus proposed that the Earth was not the center of the universe, but rather it revolved around the sun. This was a groundbreaking idea that would forever change our understanding of the cosmos. The shift from a geocentric to a heliocentric model was just the beginning. In the early 20th century, Einstein's theory of relativity revealed a universe far more bizarre than anyone had ever imagined. The idea that space and time could bend and warp under the influence of gravity was radical and difficult to grasp, but it opened the door to an entirely new way of thinking about the universe. Space and time were no longer fixed entities. They were fluid, dynamic, and intertwined. This new understanding of the cosmos shattered the old Newtonian views and laid the foundation for a new era of scientific discovery. Yet, even with these groundbreaking advancements, the universe remains shrouded in mystery. We've observed distant galaxies, studied the properties of black holes, and even launched missions to other planets. Yet there is still so much that we don't understand. Every answer seems to lead to more questions. It's as though the universe is teasing us, revealing just enough to spark our curiosity, but withholding its deepest secrets. And perhaps that is the true nature of the universe, not something to be fully understood, but something that invites us to explore and to wonder. Take, for example, the concept of the observable universe. In 1929, the astronomer Edwin Hubble discovered that the universe was expanding. This was an extraordinary finding, suggesting that the universe itself was stretching, carrying galaxies further apart. But what does this mean? If the universe is expanding, what is it expanding into? We've always assumed that space is empty, a vacuum that contains nothing but stars, planets, and galaxies. But the concept of expansion suggests that there is something beyond what we can observe, a vast, incomprehensible unknown. In fact, the universe might be much larger than we can even detect. What if there are parts of the universe that are simply beyond our reach? Areas so distant that even light from those regions hasn't had enough time to reach us, given the finite speed at which light travels. Now, consider the question of the universe's shape. For much of our history, we believed that the universe was flat, or perhaps a sphere, a neatly ordered and symmetrical shape. But recent observations have thrown this assumption into doubt. In the 1990s, scientists studying the cosmic microwave background radiation, the afterglow of the Big Bang, discovered something unexpected. The universe may not be flat at all. Instead, it could be curved, forming a vast three-dimensional shape that we cannot easily visualize. This curvature could be subtle on the scale of billions of light years, but it would fundamentally change our understanding of space itself. The very geometry of the universe, something we take for granted, could be completely different from what we assumed. If space is curved, how does that affect the way we view time, gravity, or even the way galaxies move? Perhaps most intriguingly, there are forces in the universe that we can't even see. We know that matter makes up the stars and planets, and we can observe the light emitted by these objects. But when we look more closely, we find that the visible matter in the universe only accounts for a small fraction of its total mass. The rest is invisible, undetectable to our current instruments. This is known as dark matter, a mysterious substance that interacts with gravity but not with light, making it invisible to our telescopes. Scientists first inferred its existence by observing the way galaxies rotate. Without dark matter, the galaxies should fly apart due to the lack of enough visible mass to hold them together. But dark matter, although we can't see it, exerts gravitational pull, keeping galaxies intact. And then there is dark energy, another force that has been revealed in the past few decades. Unlike dark matter, which exerts a pull on galaxies, dark energy is pushing them apart. In the late 20th century, scientists made a shocking discovery. The universe's expansion is not slowing down, as we once thought, but speeding up. Something is driving this accelerated expansion, and that something is dark energy. While dark matter is an invisible substance that helps hold galaxies together, dark energy is an invisible force that causes the universe to expand at an ever-increasing rate. Together, these two forces, dark matter and dark energy, make up around 95% of the universe, and yet we have almost no idea what they are or how they work. This brings us to the question, how much do we really understand about the universe? For all our advancements, we are still only scratching the surface of what's out there. We've mapped the stars, measured the distances to distant galaxies, and even detected the faint signals from the earliest moments of the universe. But there is so much more we have yet to discover. The very fabric of space-time itself is still largely a mystery, and there are countless unknowns that scientists are still struggling to understand. Perhaps one of the most intriguing mysteries of the universe is the question of life beyond Earth. For centuries, we've wondered whether we are alone in the cosmos. In the past few decades, the discovery of exoplanets, planets orbiting stars outside our solar system, has opened up new possibilities for finding life elsewhere. Some of these planets are located in the habitable zone, the region around a star where conditions might be right for liquid water to exist. But even with these exciting discoveries, we still don't know if life exists beyond our planet. The Fermi paradox, named after the famous physicist Enrico Fermi, asks a simple question. If the universe is so vast and full of potential, why haven't we found any evidence of extraterrestrial life? The search for life, and the possibility that we may not be alone, adds another layer of mystery to an already bewildering universe. If life does exist elsewhere, it could be radically different from anything we can imagine. Perhaps it doesn't rely on the same biochemical processes as life on Earth, or maybe it exists in a form that we cannot even detect with our current technology. The discovery of extraterrestrial life would force us to reconsider our place in the universe and our understanding of what life itself truly is. As we continue to explore the cosmos, we'll uncover more questions than answers. The universe is a vast, ever-expanding mystery that refuses to be fully understood. With each new discovery, we are forced to re-examine our assumptions and open our minds to the possibility that everything we think we know could be wrong. In the end, perhaps that's the true beauty of the universe. It's not a puzzle to be solved, but a mystery to be explored, forever unfolding before us, revealing new wonders and challenges as we push further into the unknown. We may never have all the answers, but the pursuit of knowledge, the journey of discovery, is what drives us forward. The universe is not what we think it is. It's something far greater, far stranger, and far more beautiful than we could ever imagine. So, as we embark on this journey of exploration, let's remember that the mysteries of the cosmos are not barriers to our understanding, but invitations to look deeper, to ask more questions, and to uncover truths that have been hidden for eons. The universe, with all its complexity and wonder, is waiting for us to explore, and the journey is just beginning. The scale of the universe is something that defies human comprehension. It's so vast, so immense, that we, as individuals on this small blue planet, often fail to grasp just how small we really are in the grand scheme of things. When we look up at the night sky, we see stars twinkling in the distance, galaxies swirling far away, but these objects that seem so distant are actually millions or even billions of light years away. The sheer size of the universe challenges everything we know about space, time, and existence itself. To put things into perspective, let's consider the concept of light years. A light year is the distance that light travels in 1 year, about 6 trillion miles, or approximately 9.5 trillion kilometers. Light is the fastest thing in the universe. And yet, when we talk about distances between objects in space, we often use this unit of measure because even light travels vast distances in time. For example, the closest star to Earth, Proxima Centauri, is 4.24 light-years away. While that may sound like a short distance in cosmic terms, it means that light from that star takes over 4 years to reach us. If you could travel at the speed of light, it would still take you over 4 years to reach that star, just one star in the vast expanse of space. When we look beyond our solar system, the distances only get more staggering. The nearest galaxy to the Milky Way, Andromeda, is 2.5 million light-years away. That means the light we see coming from Andromeda today actually left the galaxy 2.5 million years ago. This means that when we observe distant galaxies, we are essentially looking into the past, seeing them as they were millions, even billions of years ago. The universe is like a massive time machine, and every time we peer into space, we are witnessing snapshots of an ancient, evolving cosmos. Now, let's take this a step further. The Milky Way, our home galaxy, contains over 200 billion stars. This number alone is mind-boggling. Each of these stars, in turn, is surrounded by its own system of planets, moons, asteroids, and other celestial bodies, and the Milky Way is just one galaxy. There are billions of other galaxies scattered across the universe. In fact, scientists estimate that there are roughly 2 trillion galaxies in the observable universe. Each of these galaxies contains billions of stars, and many of these stars have their own planets. This means that there are likely more planets in the universe than there are stars, and the possibilities for life, though still unknown, are astronomical. To make this scale even harder to grasp, consider this. The observable universe, that is, the part of the universe that we can see and measure, is about 93 billion light-years across. That's an incomprehensible distance, so vast that it challenges our perception of space and time. In this vast expanse, we are but a tiny speck, a mere pinprick in the grand scheme of things. And yet, this is only the observable universe, the universe we can detect with our current technology. The universe could be much, much larger, beyond our ability to detect or even imagine. What lies beyond the observable universe is an open question, one that continues to puzzle scientists and astronomers alike. The idea of the universe being so vast brings with it a sense of awe and humility. If the universe is so large, what does that mean for our place in it? Are we truly insignificant, just another random collection of atoms in an endless expanse of space? Or is there something more? Some believe that our ability to comprehend the enormity of the universe speaks to the extraordinary nature of human consciousness. After all, it is through our curiosity, our ability to look up and question what we see, that we even attempt to make sense of it all. But even with all the technological advances we've made, powerful telescopes, advanced spacecraft, and sophisticated data analysis, there are still limits to what we can observe. Our current telescopes, like the Hubble Space Telescope, allow us to see light from distant galaxies. But there are objects in the universe that emit radiation in forms we can't detect, like dark matter and dark energy. These invisible forces make up most of the universe, yet we have no direct way of seeing them. We can only infer their existence through their gravitational effects on visible matter. This means that even though we have the technology to peer deep into the cosmos, we are still only seeing part of the picture. The size of the universe also raises questions about time. The universe is not only vast, but it is also ancient. The Big Bang, the event that birthed the universe as we know it, occurred around 13.8 billion years ago. This means that the universe is much older than our planet, and the light we see from distant galaxies has traveled through time and space for billions of years to reach us. Some of the light we see today began its journey before Earth even existed. In a way, we are looking into the past, witnessing the universe as it was long before life on Earth began. This sense of time, the fact that the universe is so old and that light takes so long to travel across vast distances, makes us realize just how fleeting human existence is. Our lives are incredibly short in comparison to the age of the universe. We live on a planet that orbits a star that is about halfway through its life cycle. In the grand scheme of things, the human experience is but a blink of an eye. Yet, within that blink, we have made remarkable strides in understanding the cosmos, from the first human gaze upward to the invention of telescopes, from the discovery of the laws of physics to the launch of spacecraft exploring distant planets. We have come a long way in our pursuit of knowledge. Even as we learn more about the universe, we are constantly reminded of how little we truly know. As we look out into space, we encounter objects and phenomena that defy our understanding. For example, black holes, incredibly dense regions of space where gravity is so strong that not even light can escape, challenge our understanding of physics. These enigmatic objects warp space and time, bending the very fabric of reality itself. But even with all the research, we still don't fully understand how they work. The same goes for dark matter and dark energy, which continue to baffle scientists. They are invisible, elusive, and account for most of the mass and energy in the universe. We know they are there, but we don't know exactly what they are or how they function. Perhaps the most humbling realization of all is that despite all our advances, we are still just beginning to understand the scale of the universe. Our most powerful telescopes, like the James Webb Space Telescope, are capable of peering deeper into space than ever before, but there will always be limits to what we can see. The universe is so vast, so ancient, and so full of mystery that we may never uncover all of its secrets. And yet, that is the beauty of it. The universe is a never-ending puzzle, constantly unfolding and revealing new wonders. The more we learn, the more we realize how much we don't know, and in that uncertainty lies an infinite sense of wonder. We are a small species on a small planet in a vast universe, yet we have the ability to look up and ask questions. The scale of the universe challenges our perception of space, time, and our place in the cosmos. But it is through this challenge that we grow and discover new horizons. The universe may be beyond our full comprehension, but it is not beyond our curiosity. As we continue to explore, to ask questions, and to search for answers, we move closer to understanding the true nature of the cosmos. And in doing so, we are reminded that the universe is not just a vast, empty space. It is a place of infinite possibility, where mysteries await us at every turn. Time and space are two concepts that, for much of human history, were thought to be simple, unchanging, and fixed. For centuries, our understanding of the cosmos was governed by the idea that time moved forward in a straight line, and space existed as a static, immutable backdrop for the events of the universe. This was the worldview of classical physics, shaped by thinkers like Isaac Newton, whose laws of motion and universal gravitation provided a framework that worked for centuries. According to Newton, time was absolute, and space was simply the empty stage upon which events unfolded. But as our understanding of the universe deepened, we began to see that time and space were far more complicated than we ever imagined. In the early 20th century, Albert Einstein revolutionized our understanding of the universe with his theory of relativity. The concept of space and time as fixed, unchangeable entities was shattered. Instead, Einstein proposed that time and space were deeply interconnected and could be distorted by the presence of mass and energy. This was the birth of the idea of space-time, a four-dimensional fabric that combines the three dimensions of space with the fourth dimension of time. In Einstein's view, space and time are not separate entities, but a unified whole, and they can bend and stretch in response to the mass and energy that exist within them. This was a radical shift in how we think about the universe. At the heart of Einstein's theory of relativity is the idea that the presence of mass distorts space-time. This means that objects with mass, like stars and planets, create a sort of dent in the fabric of space-time, causing nearby objects to move in curved paths. Imagine a rubber sheet stretched tight. If you place a heavy ball in the center of the sheet, it causes a dip, and smaller objects placed near the ball will roll towards it. This is similar to how gravity works in the universe, except instead of a rubber sheet, it's the fabric of space-time that is being distorted. This insight into the nature of gravity completely upended our previous understanding of how objects interact in space. No longer was gravity simply a force pulling objects toward one another, but rather the result of a curvature in space-time itself. One of the most famous implications of this new understanding of gravity is the concept of black holes. A black hole is a region of space where the curvature of space-time becomes so extreme that not even light can escape its pull. Black holes are formed when a massive star collapses under its own gravity at the end of its life cycle, creating a singularity, a point in space where the gravitational forces are infinitely strong, and the laws of physics as we know them break down. Black holes are one of the most mysterious objects in the universe, as they are invisible to our direct observation. We can't see them because no light can escape, but we can detect their presence by observing their effects on nearby matter. For example, when a star orbits a black hole, it experiences a gravitational pull that can cause it to move in strange elliptical orbits. By studying these orbits, scientists can infer the presence of a black hole, even though it cannot be seen directly. Einstein's theory also introduced the idea of time dilation, which is a fundamental aspect of the nature of time. According to relativity, time is not an absolute fixed quantity. It can be affected by the speed at which an object is moving or the strength of the gravitational field it is in. This means that time moves more slowly in stronger gravitational fields or at higher speeds. For example, if you were to travel near the speed of light, time would appear to slow down for you relative to someone who remained stationary. This effect, known as time dilation, has been confirmed in numerous experiments, such as those involving atomic clocks on fast-moving jets. The clocks on the jets ticked more slowly than those on the ground, just as Einstein predicted. One of the most mind-boggling consequences of this is the idea of time travel. While time travel into the future is theoretically possible based on the principles of relativity, traveling backward in time presents far greater challenges. If time is a dimension like space, then theoretically, it should be possible to move backward along the time axis, just as we can move forward through space. However, the equations of general relativity suggest that the conditions needed to travel backward in time, such as the existence of wormholes or other exotic forms of spacetime, might require circumstances that are beyond our current technological capabilities, or perhaps even beyond the laws of physics as we understand them. Another key aspect of the theory of relativity is the concept of space-time curvature. The idea that mass and energy can curve space-time is not just an abstract theoretical concept, it has practical consequences. One of the most famous experiments that confirmed Einstein's theory was the observation of light bending around the sun. When light passes near a massive object like the sun, the curvature of space-time caused by the sun's gravity causes the path of the light to bend. This phenomenon, known as gravitational lensing, has been observed many times, and it provides compelling evidence that mass and energy truly do curve space-time. Gravitational lensing has allowed scientists to study distant galaxies and other cosmic phenomena by observing how their light is bent as it travels through space. In some cases, gravitational lensing has even allowed astronomers to detect exoplanets and other objects that would otherwise be invisible. But what does this mean for our understanding of the universe? It means that time and space are not as simple and straightforward as we once believed. They are dynamic, flexible, and deeply connected to the matter and energy that fill the universe. In a sense, the fabric of space-time is like a living, breathing entity that reacts to the presence of mass and energy. The universe is not a static backdrop against which events unfold. It is an active, constantly evolving system shaped by the forces that govern it. Einstein's theory also raised new questions about the nature of the universe itself. If space and time are connected and can be distorted, what does this mean for the shape of the universe? Is the universe finite, or does it go on forever? Is it possible that the universe has a boundary, or is it infinite? with no end? These questions have long been the subject of debate among cosmologists, and the answers remain elusive. Some theories, like the concept of a multiverse, suggest that our universe is just one of many, each with its own laws of physics and its own version of space and time. If this is the case, then the nature of time and space could be radically different in other universes, further complicating our understanding of the cosmos. Despite all that we've learned about the nature of time and space, there is still much we don't understand. There are phenomena like dark matter and dark energy that we know exist because of their gravitational effects, but we can't directly observe them. We don't fully understand how they interact with space-time or what their true nature is. And then there's the question of quantum mechanics. While relativity describes the large-scale structure of the universe, quantum mechanics governs the behavior of particles at the smallest scales. At the intersection of these two realms, we find paradoxes and contradictions that challenge our understanding of reality. For example, quantum particles can exist in multiple states at once, a phenomenon known as superposition. Yet, when we try to combine this behavior with the smooth, continuous nature of spacetime described by relativity, we run into difficulties. The search for a theory that can unify quantum mechanics and general relativity, a theory of quantum gravity, is one of the greatest challenges in modern physics. The nature of time and space is not just a theoretical question. It has real-world implications for how we understand the universe and our place in it. It affects everything from the motion of planets and the behavior of black holes to the very flow of time itself. And as we continue to push the boundaries of our understanding, we are likely to uncover even more surprising and unexpected truths about the cosmos. The more we learn, the more we realize that the universe is far stranger and more complex than we could ever have imagined. The nature of time and space is just one piece of the puzzle, and as we continue to explore, we will uncover new mysteries that will challenge everything we think we know. For all the advancements we've made in our understanding of the cosmos, one of the most confounding mysteries we've encountered is something we can't even see. It's called dark matter, and it is one of the most elusive and enigmatic substances in the universe. It doesn't emit, absorb, or reflect light, which means it is invisible to our current observational tools. And yet, despite its invisibility, scientists have known about dark matter for nearly a century. They've observed its gravitational effects on visible matter, and from these effects, they are certain that it constitutes a significant portion of the universe's total mass. In fact, dark matter makes up about 27% of the universe's total mass energy content, yet it remains one of the greatest unknowns in modern physics. The concept of dark matter first emerged in the 1930s, thanks to the work of Swiss astronomer Fritz Zwicky. Zwicky was studying the Coma galaxy cluster, a group of galaxies bound together by gravity. He noticed something strange. The galaxies within the cluster were moving much faster than expected based on the visible mass of the cluster. According to Newton's laws of gravity, the galaxies should have been moving slower and the cluster should have been flying apart. Zwicky concluded that there must be some unseen mass, something invisible that was exerting a gravitational pull on the galaxies, holding them together. He called this mysterious substance dark matter, though the name wouldn't become widely accepted for several decades. In the years following Zwicky's discovery, astronomers began to notice similar discrepancies in other galaxy clusters and in the rotation curves of individual galaxies. When scientists studied the motion of stars in the outer regions of galaxies, they found that the stars were moving much faster than they should have been, given the visible mass of the galaxy. According to Newtonian physics, the stars at the edges of galaxies should be moving slower, as they are farther from the center and therefore should experience less gravitational pull. However, observations showed that they were moving at speeds that suggested there was more mass present in the galaxy than could be accounted for by visible matter alone. This was more evidence of dark matter, an invisible substance that was exerting gravitational influence but was otherwise undetectable. Dark matter is not just a theoretical concept, its existence has been supported by a variety of different observations and experiments. One of the most compelling pieces of evidence comes from the study of gravitational lensing. Gravitational lensing occurs when light from a distant object, like a galaxy or a star, is bent as it passes through the gravitational field of a massive object, like another galaxy or a galaxy cluster. The amount of bending depends on the mass of the object causing the lensing. By studying the way light is bent, scientists can estimate the mass of the intervening object. In the case of many galaxy clusters, the mass inferred from gravitational lensing is much greater than the mass that can be accounted for by the visible matter in the cluster. This is another indication that dark matter exists and makes up the missing mass. Dark matter has also been implicated in the formation of galaxies and the large-scale structure of the universe. According to the current model of cosmology, the early universe was filled with a nearly uniform distribution of matter and energy. However, small fluctuations in this distribution eventually grew into the large-scale structures we see today, like galaxies and clusters of galaxies. These fluctuations were driven in part by the gravitational pull of dark matter. In the early universe, dark matter provided the gravitational framework that allowed ordinary matter to clump together, eventually forming the galaxies and clusters we observe today. Without dark matter, it's likely that galaxies would never have formed, and the universe would be an entirely different place. Despite the overwhelming evidence for the existence of dark matter, we still don't know what it actually is. The leading candidates for dark matter are a class of hypothetical particles known as WIMPs, or weakly interacting massive particles. WIMPs are predicted to interact only through gravity and the weak nuclear force, which means they would be very difficult to detect. Because they don't interact with light, they are invisible to our telescopes. However, scientists are actively searching for WIMPs using a variety of methods, including direct detection experiments, which aim to observe the rare interactions between WIMPs and normal matter. So far, no conclusive evidence of WIMPs has been found, but the search continues. Another possible candidate for dark matter is axions, a type of hypothetical particle that is even lighter than WIMPs. Axions are predicted to interact very weakly with normal matter, and like WIMPs, they would be invisible to conventional telescopes. Axions could be detected through their effects on the cosmic microwave background radiation, the afterglow of the Big Bang, or by observing how they might affect the behavior of light. Though axions are still theoretical, they are one of the most intriguing possibilities in the search for dark matter. There is also the possibility that dark matter is not composed of particles at all, but is instead a manifestation of some new type of physics. Some theories suggest that dark matter could be explained by modifications to our understanding of gravity. For example, the theory of MOND, modified Newtonian dynamics, proposes that the laws of gravity may behave differently at extremely large scales, where dark matter is most apparent. According to MOND, the anomalous motion of stars and galaxies and clusters could be explained by a modification of gravity rather than the presence of unseen matter. However, while MOND has had some success in explaining certain observations, it has not been able to explain all the evidence for dark matter, particularly the effects seen in galaxy clusters and gravitational lensing. Despite these efforts, dark matter remains elusive. We are still in the early stages of understanding its nature, and much more research is needed to uncover the true identity of this invisible substance. Scientists are exploring new ideas and conducting experiments with cutting-edge technology in hopes of solving one of the most profound mysteries of the universe. The discovery of dark matter would not only provide insight into the composition of the universe, but also open up entirely new realms of physics, challenging our most fundamental ideas about the laws of nature. One of the key challenges in understanding dark matter is that it does not emit, absorb, or reflect light, making it impossible to detect using conventional telescopes. Instead, scientists rely on indirect methods to detect its presence, such as observing the gravitational effects it has on visible matter. This reliance on indirect evidence has led to some controversy within the scientific community. Some scientists argue that dark matter may be an unnecessary hypothesis and that the observations can be explained by modifications to our understanding of gravity. However, the overwhelming evidence from galaxy rotation curves, gravitational lensing, and the cosmic microwave background radiation suggests that dark matter is real, and its influence on the universe is profound. In the meantime, the search for dark matter continues. With each passing year, scientists are coming closer to understanding its nature. New experiments and observations are being conducted at facilities around the world, and the advent of new technologies, like the Large Hadron Collider, is offering new insights into the fundamental particles and forces of the universe. In addition, space telescopes like the James Webb Space Telescope, which will soon be launched, will provide a new perspective on the distant universe, offering the potential to uncover new clues about dark matter. The mystery of dark matter is a reminder of just how much we still have to learn about the universe. Despite all our technological advancements and scientific discoveries, the cosmos continues to surprise us with its complexity and its secrets. Dark matter is just one of the many enigmas that we will need to solve as we continue our journey of exploration. And as we seek answers to these cosmic questions, we will undoubtedly uncover even more mysteries, each more profound and fascinating than the last. The search for dark matter is far from over, but the quest for knowledge, the desire to understand the universe and our place within it, will continue to drive us forward ever deeper into the unknown. While dark matter remains one of the most perplexing mysteries of the universe, it is far from the only invisible force driving the cosmos. Equally as baffling and just as elusive is dark energy, a phenomenon that, despite being one of the most profound discoveries in cosmology, still eludes our understanding. The concept of dark energy challenges everything we thought we knew about the nature of the universe, yet its discovery has led scientists to one of the most remarkable realizations of the modern era. The universe is expanding at an accelerating rate. The discovery of dark energy dates back to the late 1990s, when two independent teams of astronomers, led by Saul Perlmutter, Brian Schmidt, and Adam Rees, were studying the light from distant supernovae. These supernovae, which are the explosive deaths of massive stars, were thought to be reliable standard candles, objects whose intrinsic brightness is well known, allowing astronomers to calculate their distance from Earth. The assumption was that the universe's expansion, which had been occurring since the Big Bang, was slowing down over time due to gravity, the pull of galaxies on one another. This deceleration seemed inevitable, given the vast amount of matter in the universe. However, when these astronomers measured the brightness of the distant supernovae, they were stunned. Instead of finding that the expansion was slowing down, they discovered that it was accelerating. This was completely unexpected and completely contradictory to what had been theorized. Initially, this revelation was met with skepticism. It was hard to imagine a force that could accelerate the expansion of the universe, especially one that could overpower the gravitational pull of galaxies and other large structures. Yet, after further analysis, the evidence became undeniable. Something was causing the expansion of the universe to speed up, and this something was later named dark energy. Dark energy, like dark matter, is invisible to our senses. It doesn't emit, absorb, or reflect light, and it cannot be detected by traditional telescopes. Despite its elusiveness, dark energy is believed to make up about 70% of the total energy content of the universe. In fact, it is the dominant force driving the cosmos. While dark matter influences the motion of galaxies and the formation of cosmic structures, dark energy is responsible for the accelerated expansion of the universe. But unlike dark matter, which works through gravity, dark energy acts in the opposite way. It seems to push galaxies apart, causing the universe to stretch at an ever-increasing rate. To understand why this is so strange, we need to think about the expansion of the universe. Since the Big Bang, the universe has been expanding. The galaxies are moving away from one another, with space itself stretching between them. Initially, this expansion was expected to slow down over time as gravity, the force of attraction between masses, would naturally pull matter back together. In fact, For much of the universe's history, gravity dominated, causing galaxies to move slower as they moved away from each other. However, the discovery of dark energy has upended this idea, suggesting that the universe is actually being pushed apart not by gravitational attraction, but by an unseen repulsive force. The way we now understand dark energy is based on its impact on the large-scale structure of the universe. In the early days of cosmology, the universe was seen as relatively homogeneous, with galaxies scattered throughout space in a more or less uniform distribution. Over time, however, matter began to clump together due to the gravitational attraction between galaxies and other cosmic structures. Dark matter helped facilitate this clustering, and gravity was expected to keep it all from flying apart. Yet, this clumping of matter and the overall slowing down of the universe's expansion was not to be. Instead, dark energy came into play, exerting a force that has caused the expansion of the universe to accelerate. One of the most perplexing aspects of dark energy is its nature. While scientists know its effects, they don't know what it actually is. There are several competing theories about the origin and properties of dark energy, but no one knows for sure which, if any, is correct. One of the most popular explanations is related to the concept of the cosmological constant, a term introduced by Albert Einstein in his equations of general relativity. Einstein originally included this constant to allow for a static, unchanging universe, a view that was widely accepted at the time. However, when it was later discovered that the universe was expanding, Einstein abandoned the cosmological constant, famously calling it his biggest blunder. In the context of dark energy, the cosmological constant has made a comeback. The idea is that dark energy could be a property of space itself, a kind of energy inherent to the fabric of space-time. This constant energy density would cause space to expand more and more rapidly as the universe ages. Essentially, the more space there is, the more dark energy there is, leading to an ever-accelerating expansion. While this theory is appealing, it raises its own set of questions. For example, why has this energy remained constant over the entire history of the universe? Shouldn't the density of dark energy decrease as the universe expands? Another theory suggests that dark energy could be a result of quantum fluctuations in the vacuum of space. According to quantum mechanics, even empty space is not truly empty, but is instead filled with fleeting particles that constantly pop in and out of existence. These quantum fluctuations could contribute to the repulsive force we observe as dark energy. However, this theory also faces challenges. The energy predicted by quantum mechanics for these fluctuations is far too large to match the amount of dark energy that has been observed, by many orders of magnitude. This discrepancy is one of the greatest unresolved problems in modern physics, often referred to as the cosmological constant problem. Some theories also suggest that dark energy might be tied to the properties of scalar fields, which are theoretical fields that permeate space and exert a force on matter. These scalar fields could vary in strength over time or space, potentially explaining the accelerated expansion of the universe. The challenge here is that no one has yet found concrete evidence of such fields. Despite these various hypotheses, the true nature of dark energy remains one of the most pressing mysteries in cosmology. Understanding dark energy is crucial because it has profound implications for the ultimate fate of the universe. If dark energy continues to accelerate the expansion of the universe, it could lead to a big rip, a scenario in which galaxies, stars, planets, and even atoms are torn apart as the expansion accelerates exponentially. This fate, however, is still speculative, and the actual outcome of dark energy's influence is still uncertain. Some scientists propose that dark energy might eventually weaken, causing the universe's expansion to slow down and reverse, leading to a big crunch where the universe collapses in on itself. But this is purely hypothetical, and current observations suggest that the acceleration of the universe's expansion is continuing, making a big rip more likely. Another fascinating possibility is that dark energy could be related to the multiverse theory. In this view, the accelerated expansion of our universe could be part of a larger cosmic process where multiple universes are born and die in a vast, ever-expanding multiverse. In this model, dark energy is the force that drives the creation of new universes. While this idea remains speculative, it raises intriguing questions about the very nature of existence and whether our universe is just one of many. Despite the many questions and the uncertainty surrounding dark energy, one thing is clear. This invisible force is shaping the future of the universe in ways we are only beginning to understand. Its discovery has fundamentally altered our conception of the cosmos, and it has opened up new avenues of exploration and inquiry. Understanding dark energy is essential for understanding the fate of the universe itself, whether it will continue to expand forever, collapse, or reach some other unexpected end. The search for answers to the dark energy enigma is ongoing. Every new observation, every new experiment, brings us closer to understanding the forces that govern the cosmos. As scientists continue to study the universe's expansion and explore the nature of dark energy, they will undoubtedly uncover even more surprises that will challenge our assumptions and deepen our understanding of the universe. The accelerating expansion of the universe is one of the most profound discoveries of modern cosmology, and the journey to understand dark energy is just beginning. The multiverse theory, one of the most fascinating and mind-bending ideas in modern cosmology, proposes that our universe is just one of countless others, each with its own distinct laws of physics, dimensions, and realities. This concept stretches our imagination to its limits, suggesting that the universe we know may be far smaller and more limited than we ever realized. According to the multiverse hypothesis, the universe we live in is merely one bubble in a vast cosmic sea of other bubbles, each containing its own separate universe. The idea of multiple universes has fascinated scientists and philosophers alike for decades, but it wasn't until the development of quantum mechanics and string theory that the concept began to take shape in the realm of scientific possibility. At the heart of the multiverse theory lies the idea that there are many different universes, each with its own set of physical laws and constants. The notion that there could be more than one universe has a long history, but it wasn't until the 20th century that serious scientific theories began to support the idea. Some of the first inklings of a multiverse came from quantum mechanics, the branch of physics that deals with the behavior of particles at the smallest scales. Quantum mechanics is filled with strange and counterintuitive concepts, such as superposition, where particles can exist in multiple states at once, and entanglement, where particles can be instantaneously connected to one another across vast distances. These bizarre phenomena led some physicists to speculate that the universe itself could have a more complex structure than we initially thought, potentially involving multiple parallel realities. The idea of the multiverse is often discussed in connection with the theory of cosmic inflation. Cosmic inflation is the theory that the universe underwent an incredibly rapid expansion just after the Big Bang, growing exponentially in size in a fraction of a second. According to this theory, during this brief period of rapid expansion, small quantum fluctuations in the early universe could have been stretched to enormous scales, leading to the formation of many separate pocket universes, each with its own unique properties. These pocket universes would be disconnected from one another, each evolving independently according to its own physical laws and constants. This theory suggests that the Big Bang we observe in our universe might not have been a one-time event, but rather part of a never-ending cycle of cosmic births. Each time a new universe is created, it experiences its own Big Bang and begins its own journey of expansion. This concept of eternal inflation proposes that our universe is just one of many, with each universe in the multiverse experiencing its own separate history and destiny. Some universes could have different physical constants, such as the strength of gravity or the mass of fundamental particles, leading to entirely different kinds of physical realities. In some universes, life may not be possible at all, while in others, the laws of physics could be radically different, giving rise to strange and exotic forms of matter and energy. String theory, another theoretical framework in modern physics, provides further support for the idea of a multiverse. String theory posits that the fundamental building blocks of the universe are not point-like particles, as previously thought, but rather tiny, vibrating strings of energy. These strings can exist in multiple dimensions, and the way they vibrate determines the types of particles and forces that exist in our universe. However, string theory also suggests that there are more than the familiar three dimensions of space and one dimension of time that we experience in our everyday lives. According to string theory, the universe could have as many as 10 or 11 dimensions, many of which are hidden from our perception. Some versions of string theory propose that different universes could exist in different regions of these higher dimensional spaces, each with its own set of physical laws and properties. These universes would be fundamentally separate from each other, but could still be linked in ways that we are not, yet able to comprehend. One of the most fascinating aspects of the multiverse theory is the possibility that there are universes with entirely different laws of physics. In our universe, the laws of physics are finely tuned to allow for the existence of stars, planets, and life. The strength of gravity, the mass of electrons, and the properties of fundamental forces all appear to be perfectly balanced to make life possible. But what if these constants were different in other universes? What if the strength of gravity was much stronger or weaker, or if the fundamental forces operated in ways that we can't even imagine? In such universes, the very concept of life might be impossible, or it might take forms that are radically different from anything we know. Some theorists even propose that there could be universes where the laws of physics themselves are completely different, creating realities that are completely alien to our understanding. The implications of the multiverse theory are profound. If there are infinite universes, it raises the possibility that every conceivable outcome of every event happens somewhere in the multiverse. This means that in one universe, you may have made a different decision, taken a different path in life, or even experienced a different version of yourself. The idea of parallel universes, where different versions of ourselves exist in different realities, is a staple of science fiction, but the multiverse theory suggests that this could be more than just fiction. It suggests that every possible outcome, every choice, every event, every possibility could be realized somewhere in the vast expanse of the multiverse. But if there are infinite universes, does that mean anything is possible? Could there be universes where the fundamental constants of nature are so different that the very nature of reality is unrecognizable? Could there be universes where the laws of physics allow for time travel, teleportation, or even the manipulation of reality itself? The possibilities seem endless. Some scientists speculate that there could be universes with entirely different forms of matter and energy, or even universes where the concept of time itself does not exist in the way we understand it. In these universes, the very rules of existence could be different from anything we could imagine, creating strange and bizarre realities beyond our wildest dreams. Despite the intriguing possibilities, the multiverse theory is not without its critics. One of the biggest challenges in proving the existence of other universes is that they are, by definition, unobservable. If other universes exist outside our own cosmic bubble, we have no way of detecting them directly. Some argue that the multiverse theory is purely speculative, with no empirical evidence to support it. Critics also point out that the theory may not be testable, meaning that it could fall into the realm of science fiction rather than science itself. Without the ability to make predictions or conduct experiments that could confirm or refute the existence of other universes, some scientists believe that the multiverse theory cannot be considered a legitimate scientific theory. However, there are those who believe that the multiverse theory is more than just a speculative idea. They argue that it is a natural consequence of well-established theories like cosmic inflation and string theory. Even though we cannot directly observe other universes, they suggest that indirect evidence, such as the patterns in the cosmic microwave background radiation or the distribution of galaxies, could provide clues to the existence of the multiverse. Additionally, As our understanding of quantum mechanics and higher dimensional physics continues to evolve, new ways of testing the multiverse hypothesis may emerge. Whether or not the multiverse exists, the idea of multiple universes raises important philosophical and metaphysical questions. If there are infinite realities, what does this mean for the nature of existence? Are we simply one version of reality among countless others, or is our universe unique? Does the existence of multiple universes imply that everything is predetermined, or that every possibility is realized somewhere in the multiverse? These questions challenge our deepest assumptions about the nature of life, the universe, and our place within it. The multiverse theory also opens up exciting possibilities for the future of science and exploration. If other universes exist, it suggests that there could be a vast and infinite cosmic landscape waiting to be explored. And while we may never be able to visit these other universes, the very idea that they might exist forces us to think differently about our own universe and the limits of our knowledge. As we continue to explore the cosmos, the multiverse theory will undoubtedly remain a key area of interest. Whether we ever find direct evidence of other universes or not, the possibility that our universe is just one of many will continue to inspire wonder, curiosity, and speculation. In the end, the multiverse theory invites us to expand our minds and imagine a reality far more complex and vast than we ever imagined, a reality in which the possibilities are truly infinite. The question of whether we are alone in the universe is one of the oldest and most profound questions humanity has asked. For millennia, civilizations have pondered the possibility of life beyond Earth, crafting myths and stories about beings from other worlds. The search for extraterrestrial life has always been more than just a scientific endeavor. It is a quest to understand our place in the vast expanse of the cosmos. Are we, as the human race, the only intelligent beings in this enormous universe, or is there life out there waiting to be discovered? The question of extraterrestrial life has intrigued scientists for centuries. As early as the ancient Greeks, philosophers speculated that life might exist on other planets. In the 16th and 17th centuries, astronomers such as Johannes Kepler and Galileo Galilei used telescopes to study the night sky, leading them to propose the idea that the stars might be like our own sun, with planets orbiting around them. But it wasn't until the 20th century that the idea of extraterrestrial life began to take shape within the framework of modern science. The discovery of thousands of exoplanets, planets that orbit stars outside our solar system, has transformed our understanding of the universe and opened up new possibilities for the existence of life elsewhere. In the mid-20th century, scientists began to take a more systematic approach to the search for extraterrestrial life, leading to the development of the field known as astrobiology. Astrobiology is the study of the conditions under which life might arise elsewhere in the universe, and the search for signs of life on other planets and moons. As the field of astrobiology grew, scientists began to look for biosignatures, signs of life, whether microbial or more complex, in distant environments. For much of the 20th century, the search focused on the surface of Mars, a planet that, in some ways, seems similar to Earth. The idea that life might have once existed on Mars, or might still exist in some form today, became one of the primary goals of space exploration. The first serious search for life on Mars took place with the Viking missions in the 1970s. NASA's Viking landers conducted experiments on the Martian soil, looking for evidence of microbial life. Although the results were inconclusive, the possibility that life might have existed on Mars remained. Since then, numerous missions to Mars, including the rover Spirit, Opportunity, Curiosity, and Perseverance, have sought evidence of ancient water, organic molecules, and other biosignatures that might indicate life. In recent years, scientists have found evidence of liquid water in the form of seasonal brine flows on the surface of Mars, leading to renewed hopes that microbial life might still exist, hidden beneath the planet's cold, arid surface. But Mars is not the only place in our solar system where scientists are looking for signs of life. Moons like Europa, Enceladus, and Titan, which orbit the gas giants Jupiter and Saturn, are considered some of the best candidates for the existence of extraterrestrial life within our own solar system. Europa, one of Jupiter's moons, is believed to have a vast subsurface ocean beneath its icy crust. Scientists speculate that this ocean could harbor microbial life, particularly because Europa is thought to have the necessary chemical ingredients for life, such as liquid water and organic molecules. Similarly, Enceladus, one of Saturn's moons, has been observed ejecting geysers of water vapor, indicating the presence of a subsurface ocean that could also support life. Titan, Saturn's largest moon, has long been a subject of fascination for astrobiologists. Unlike the cold, ice-covered moons of Jupiter, Titan is a world of methane lakes and rivers with a thick, nitrogen-rich atmosphere. Though Titan's conditions are vastly different from those on Earth, scientists believe that its unique chemistry could potentially give rise to a form of life vastly different from anything we know. In 2005, the Huygens probe, part of the Cassini mission, landed on Titan's surface, providing the first direct measurements of this alien world. The discovery of organic molecules on Titan and the presence of liquid methane lakes suggest that Titan could be a promising place to search for signs of life. Beyond our solar system, the search for extraterrestrial life has taken on a new dimension with the discovery of thousands of exoplanets, planets that orbit stars outside our solar system. Since the first confirmed discovery of an exoplanet in the 1990s, astronomers have found more than 5,000 confirmed exoplanets, with thousands more awaiting confirmation. Many of these exoplanets are located in the habitable zone of their host stars, the region where conditions might be right for liquid water to exist, a key ingredient for life as we know it. Some of these planets are similar in size to Earth, and scientists are now focused on finding Earth-like planets that might support life. The discovery of potentially habitable exoplanets has sparked excitement in the scientific community, as it increases the likelihood that life exists elsewhere in the universe. One of the most notable discoveries is that of Proxima b, a planet that orbits Proxima Centauri, the closest star to our Sun. Proxima b is located in the habitable zone of its star, meaning that it could potentially support liquid water. Though much more research is needed to determine whether Proxima b has the necessary conditions for life, its discovery has made scientists even more hopeful about the possibility of finding extraterrestrial life. In addition to searching for signs of life on exoplanets, astronomers are also looking for technosignatures, signs of advanced civilizations that might be detectable through their technological activity. The search for extraterrestrial intelligence, or SETI, has been underway for decades, aiming to detect radio signals or other forms of communication from intelligent beings in other star systems. While SETI has not yet found any conclusive evidence of extraterrestrial civilizations, the search continues. In recent years, the discovery of fast radio bursts, mysterious, powerful bursts of radio waves from distant galaxies, has prompted speculation that some of these signals could be of extraterrestrial origin, though they are more likely to be natural phenomena. The possibility that extraterrestrial life could exist elsewhere in the universe raises profound philosophical questions. If we were to find life on another planet, what would it mean for our understanding of ourselves and our place in the cosmos? Would the discovery of alien life challenge our beliefs about the uniqueness of Earth and humanity? And if we were to find intelligent life, what implications would that have for our future as a species? The search for extraterrestrial life is not just about finding other forms of life. It is about understanding our own origins, our purpose in the universe, and the nature of existence itself. One of the most intriguing aspects of the search for extraterrestrial life is the possibility that life elsewhere might be very different from life on Earth. Life on Earth is based on carbon chemistry, with water as a solvent, and our biology is shaped by the unique conditions of our planet. However, scientists have speculated that life could exist in forms that are radically different from what we know. Perhaps extraterrestrial life could be silicon-based, or it could exist in environments that are inhospitable to us, such as the extreme temperatures or acidic conditions of other planets and moons. The possibilities for what life could look like are limited only by our imagination. The discovery of extraterrestrial life would be one of the most profound moments in human history, changing our understanding of the universe and our place within it. However, even if we do not find life beyond Earth, the search itself has taught us valuable lessons about the resilience of life, the adaptability of organisms, and the preciousness of our own planet. It has also driven us to develop new technologies and methodologies, pushing the boundaries of space exploration and scientific discovery. As we continue to look beyond our world, we are reminded that the universe is vast and full of mysteries waiting to be unraveled. So, are we alone in the universe? The answer to that question remains unknown, but the search for life beyond Earth is far from over. With each new discovery, whether on Mars, Europa, or distant exoplanets, we move closer to answering one of the most fundamental questions of human existence. The search for extraterrestrial life is not just a quest to find other beings. It is a quest to understand life itself, to explore the limits of possibility, and to discover the true nature of the cosmos. As we venture further into the mysteries of the cosmos, one stark reality becomes increasingly evident. The limits of human knowledge are far greater than we would like to admit. Despite centuries of discovery, the progress we've made in understanding the universe is like a mere scratch on the surface of what there is to know. We live in a time of remarkable scientific achievement, a time when we can peer into the depths of space with the help of powerful telescopes, explore distant planets with rovers, and even observe the bending of light through gravitational lensing. But despite these advancements, we are still confronted by vast, impenetrable gaps in our understanding. The question of how much we truly know is not just a philosophical one. It is a fundamental issue in the history of science. For centuries, we believed that the universe was finite and contained within clear, fixed boundaries. Early astronomers believed that the Earth was the center of the universe and that the stars, planets, and sun all revolved around it in perfectly circular orbits. This geocentric model of the universe stood unchallenged for over 1,000 years. It wasn't until the 16th century, with the work of Copernicus, that this view began to be shattered. Copernicus proposed the heliocentric model, suggesting that the sun, not the Earth, was at the center of the solar system. This idea, though radical, eventually gave way to our modern understanding of the universe, a universe where planets orbit stars, and stars themselves are part of vast galaxies that are spread out across an expanding cosmos. Yet, as we learned more about the universe, the more we realized how little we truly understood. The discovery of the vastness of the universe, for example, raised new questions about its scale, its origin, and its ultimate fate. In the early 20th century, Edwin Hubble made the groundbreaking observation that galaxies were moving away from us in all directions, suggesting that the universe itself was expanding. This led to the development of the Big Bang theory, which proposed that the universe began as a singularity, a point of infinite density and temperature, and has been expanding ever since. But what caused the Big Bang? What was there before it? These are questions that remain unanswered to this day. Despite our advancements, we still do not have a unified theory of everything, a theory that can explain all of the fundamental forces of nature in a single framework. Physics is divided into two main domains: general relativity, which describes the force of gravity and governs the behavior of large-scale objects like planets, stars, and galaxies, and quantum mechanics, which governs the behavior of the smallest particles in the universe. These two theories have been incredibly successful in their respective domains, but they are fundamentally incompatible. General relativity describes space-time as a smooth, continuous fabric, while quantum mechanics suggests that space-time is quantized, made up of discrete units. The challenge is to reconcile these two vastly different descriptions of reality into a single unified theory. The search for such a theory, often referred to as quantum gravity, is one of the greatest challenges in modern physics. One of the greatest limitations in our understanding of the universe is the inability to directly observe phenomena like dark matter and dark energy. Though we have strong evidence for the existence of these mysterious forces, we have no direct way of seeing them. Dark matter, which is believed to make up about 27% of the universe, exerts gravitational pull on visible matter, but it doesn't interact with light, making it invisible to our telescopes. Similarly, dark energy, which is thought to be responsible for the accelerated expansion of the universe, remains an enigma. We can see its effects, but we have no concrete understanding of what it is or how it works. Despite all our technological advancements, these invisible forces remain beyond our direct detection. Moreover, the vast distances between us and other objects in the universe create a fundamental barrier to our knowledge. Even with the most powerful telescopes, we are limited by the speed of light. The observable universe, the part of the universe we can see, is roughly 93 billion light-years across, but this is only the part we can detect. The rest of the universe, beyond our observational reach, remains completely unknown. This means that no matter how much we learn, there will always be a vast and inaccessible portion of the cosmos that we can never observe. It's a humbling realization. The universe is simply too vast for us to ever fully comprehend, no matter how advanced our technology becomes. Beyond the challenges of the cosmos, there are also the limitations of our own understanding of the natural world. Science is a process of discovery, and for every answer we uncover, more questions seem to arise. Our understanding of life, for example, is still incomplete. Though we know the basic building blocks of life, DNA, cells, proteins, we do not fully understand how life originated on Earth, nor do we know if life exists elsewhere in the universe. The search for the origins of life, or abiogenesis, is a central pursuit in the field of astrobiology, but we still have no definitive answer to how life first emerged from the primordial soup of molecules on Earth. Was life a unique event that happened here? Or is life common throughout the universe, waiting to be discovered? The same is true for our understanding of consciousness, a topic that has fascinated philosophers and scientists alike for centuries. We know a great deal about the brain and how it functions, but the nature of consciousness, the feeling of being aware, of having thoughts and experiences, remains elusive. There is no consensus in science about how consciousness arises from the physical processes of the brain. Is consciousness simply the product of complex neural activity, or is there something more to it, something beyond the physical? Some theories propose that consciousness is a fundamental aspect of the universe, like space and time, while others suggest it is an emergent property of complex systems. However, we are still far from answering these questions definitively. Even in the realm of philosophy, where human knowledge has been refined for millennia, there are questions that remain unsolvable. The question of what is reality has been asked by philosophers since ancient times, and yet we still have no clear answer. Are we simply perceiving an illusion, or is the universe as we see it truly real? And if it is real, how can we know anything with certainty? The limitations of human perception, our subjective experience of the world, make it difficult to answer these questions with absolute certainty. Science provides us with models and theories, but those theories are always subject to revision as new evidence emerges. What we know today may be proven false tomorrow. As we confront these limitations, it's important to remember that science is a process, not a destination. The fact that we don't have all the answers does not mean that we should give up our search for knowledge. Instead, it means that we must continue to push the boundaries of what we know, exploring new frontiers and challenging old assumptions. The pursuit of knowledge is an ongoing journey, one that has led to incredible discoveries and will continue to yield new insights about the universe and our place within it. Ultimately, the limits of human knowledge are not something to despair over, but something to embrace. It is the very nature of knowledge that it is always incomplete, always evolving. The universe is vast, and there will always be things that remain beyond our grasp. But this doesn't diminish the beauty and excitement of discovery. In fact, it makes the quest for understanding all the more profound. As we continue to learn and grow, we deepen our connection to the cosmos, to the mysteries that lie within it, and to the uncharted territories of our own minds. The limitations of our knowledge are not obstacles to progress, they are invitations to explore. The more we discover, the more we realize how much there is left to know. And in that realization lies the true beauty of science. It is not about reaching the end, but about embarking on a journey that never truly ends. The more we learn, the more we understand the vastness of what we don't know, and that knowledge in itself is a reminder of the infinite mysteries that still await us. And so, we continue the search, ever driven by curiosity, knowing that the unknown will always be a part of our quest for understanding. At the core of modern physics lies a branch of science that challenges everything we think we know about the nature of reality. Quantum mechanics, a field that describes the behavior of particles at the smallest scales, has completely reshaped our understanding of the universe. It introduces a world that is far stranger than our everyday experience, one where particles can exist in multiple places at once, can be entangled over vast distances, and can behave in ways that defy logic. Yet, this strange and paradoxical realm of quantum mechanics is not only essential for explaining the behavior of the smallest particles, but is also integral to understanding the very structure of the universe itself. Quantum mechanics emerged in the early 20th century as scientists began to uncover the limitations of classical physics. Classical physics, based on the laws of Newtonian mechanics and electromagnetism, had been incredibly successful in describing the motion of macroscopic objects, things like cars, planets, and projectiles. But when scientists began to study the behavior of atoms and subatomic particles, they encountered phenomena that couldn't be explained by classical physics. Electrons orbiting around atomic nuclei, for example, didn't behave the way they should according to Newton's laws. Instead, they exhibited strange behaviors that could only be explained by a new set of rules, rules that would become known as quantum mechanics. The birth of quantum mechanics can be traced back to Max Planck, who in 1900 proposed that energy is not continuous, but rather comes in discrete packets, which he called quanta. This idea was radical at the time, as it contradicted the prevailing view that energy could be divided infinitely. But Planck's work was just the beginning. Over the next few decades, scientists like Albert Einstein, Niels Bohr, Werner Heisenberg, and Erwin Schrödinger developed the mathematical framework that would define quantum mechanics. They discovered that particles could behave both as particles and as waves, depending on how they were observed. They also found that certain properties, like an electron's position or momentum, could not be measured simultaneously with absolute precision, a concept known as the Heisenberg uncertainty principle. This principle, one of the most famous aspects of quantum mechanics, tells us that the more precisely we try to measure one property of a particle, the less precisely we can measure another. For example, if we try to measure the position of an electron with great accuracy, we lose information about its momentum. This uncertainty is not due to limitations in our measurement devices. It is a fundamental property of nature itself. It suggests that at the quantum level, the universe is inherently indeterminate, with particles existing in a range of possible states until they are observed. This idea challenges our classical intuition, where we assume that everything has a definite position and momentum at all times. One of the most astonishing features of quantum mechanics is the concept of superposition. According to this principle, particles can exist in multiple states at once. For example, an electron in an atom doesn't orbit the nucleus in a single fixed orbit. Instead, it exists in a cloud of probabilities spread out over a range of possible positions. It is only when we measure the position of the electron that it collapses into one of these possibilities. Until then, the electron is in a superposition of all possible states. This behavior is not confined to electrons. It applies to all particles, no matter how small. In fact, the phenomenon of superposition has been demonstrated with larger and larger particles, challenging our classical ideas of what constitutes reality. Perhaps the most baffling aspect of quantum mechanics is the EBI's concept of entanglement. When two particles become entangled, their properties are linked in such a way that measuring one particle's state immediately determines the state of the other, no matter how far apart the two particles are. This connection occurs instantaneously, even if the particles are separated by vast distances, a phenomenon that Albert Einstein famously referred to as spooky action at a distance. Entanglement appears to defy the speed of light, which is supposed to be the ultimate limit on the transmission of information. Yet, experiments have shown that entanglement is real, and its effects have been demonstrated in laboratories around the world. Entanglement has profound implications for our understanding of space and time. It suggests that the universe is not made up of independent, isolated particles, but rather that everything is interconnected in ways we do not fully understand. The very fabric of reality, it seems, is far more interconnected than we ever imagined. This has led some scientists to suggest that the classical view of space and time as separate entities may be an illusion. Instead, space and time might be emergent properties of a deeper, more fundamental reality. In this view, quantum entanglement might be a manifestation of a hidden, underlying structure to the universe, one that transcends the limitations of space and time. The strangeness of quantum mechanics extends to the concept of quantum tunneling. In classical physics, particles are expected to move in predictable, deterministic paths, and they cannot pass through barriers unless they have enough energy to overcome them. But in the quantum world, particles can tunnel through barriers that they don't have enough energy to cross in classical terms. This means that an electron, for example, could appear on the other side of an energy barrier, even though it should not have been able to cross it according to classical physics. Quantum tunneling is a crucial phenomenon in many processes, including nuclear fusion in stars, where particles tunnel through energy barriers to combine and release energy. This phenomenon also has applications in modern technology, such as the operation of semiconductors and tunneling microscopes. One of the most profound implications of quantum mechanics is its impact on our understanding of reality itself. The probabilistic nature of quantum mechanics suggests that the universe is not a fixed, deterministic system, but one that is constantly in flux with multiple potential outcomes. Until we observe a system, the universe exists in a superposition of all possible states, and only the act of measurement collapses this superposition into a single reality. This has led to the development of various interpretations of quantum mechanics, each attempting to explain the meaning of this strange behavior. One of the most famous interpretations is the Copenhagen interpretation, which posits that the act of measurement itself creates reality. According to this view, the wave function of a particle, a mathematical description of all its possible states, only collapses into a definite state when it is observed. Until that moment, the particle exists in a superposition of all possible states. Another interpretation, known as the many worlds theory, suggests that all possible outcomes of a quantum event actually occur, but in different parallel universes. In this view, every time a quantum measurement is made, the universe splits into multiple versions, each corresponding to a different outcome. Though these interpretations differ in their explanations, they all share a common thread. Quantum mechanics reveals a universe far stranger and more mysterious than we ever imagined. The behavior of particles at the quantum level challenges our fundamental assumptions about reality, space, and time. It suggests that the universe is not as solid and predictable as we once thought, but rather a vast interconnected web of probabilities where the act of observation itself shapes the course of events. Quantum mechanics also plays a crucial role in cosmology. The early universe, immediately after the Big Bang, was dominated by quantum effects. During this period, known as the Planck era, the universe was incredibly hot and dense, and quantum fluctuations in spacetime played a key role in shaping the universe's structure. It is believed that quantum fluctuations during the period of cosmic inflation, a brief moment of rapid expansion in the early universe, seeded the formation of galaxies and large-scale structures. These quantum fluctuations, stretched to cosmic scales, provided the initial ripples in spacetime that would eventually give rise to the galaxies, stars, and planets we see today. Quantum mechanics also offers clues to some of the biggest mysteries in cosmology. For example, the nature of black holes is still a topic of intense research, and quantum effects are thought to play a role in their behavior. The famous information paradox, the question of whether information that falls into a black hole is lost forever, is one of the most perplexing problems in modern physics. Some physicists believe that quantum mechanics holds the key to resolving this paradox and understanding what happens inside black holes. Theoretical ideas such as the holographic principle suggest that the information contained within a black hole might be encoded on its surface, leading to a deeper understanding of the relationship between quantum mechanics and gravity. In addition to cosmology, quantum mechanics has a profound impact on our understanding of the very fabric of reality. The study of quantum field theory, which describes the interaction of particles as excitations in quantum fields, is one of the most important areas of research in modern physics. This theory has led to the development of the Standard Model of particle physics, which describes the fundamental particles and forces that make up the universe. The discovery of the Higgs boson, often referred to as the God particle, in 2012, was a monumental achievement in quantum physics, confirming the existence of the Higgs field and explaining why particles have mass. Quantum mechanics is not just a field of theoretical physics, it is a technology that has already had a profound impact on our lives. Quantum mechanics is the foundation of technologies like semiconductors, lasers, and magnetic resonance imaging, MRI. The development of quantum computers, which harness the strange properties of quantum mechanics to perform calculations far beyond the capabilities of classical computers, promises to revolutionize fields ranging from cryptography to drug discovery. Quantum mechanics is not just a theoretical framework, it is a powerful tool that is shaping the future of technology and science. As we continue to probe the depths of the quantum realm, we are confronted with a universe that is both fascinating and perplexing. Quantum mechanics reveals a world that is far more complex, interconnected, and mysterious than we ever imagined. The deeper we dive into this strange world, the more we realize that our understanding of reality is just beginning. The role of quantum mechanics in shaping the universe is far from fully understood, and as we continue to explore, we will undoubtedly uncover new insights that will change our perception of the cosmos and our place within it. As we stand on the precipice of the future, looking out into the vast expanse of space, it's impossible not to feel a sense of awe at the possibilities that lie ahead. The journey of cosmic discovery is far from over. In fact, we are only just beginning to explore the mysteries of the universe. Our understanding of the cosmos has come a long way in the past few centuries, but the most exciting chapters of this journey are still unwritten. The future of space exploration and cosmic discovery promises to be filled with breakthroughs, revelations, and challenges that will reshape our understanding of reality itself. One of the most exciting areas of cosmic discovery lies in the continued exploration of our own solar system. For decades, we've looked to planets like Mars, Jupiter, and Saturn for clues about the formation of the solar system and the possibility of life beyond Earth. But there is still so much more to explore. Take, for example, the moons of Jupiter and Saturn, which are some of the most intriguing objects in our solar system. Europa, one of Jupiter's moons, is believed to harbor a subsurface ocean beneath its icy crust, and scientists are eager to explore this potential habitat for life. Similarly, Saturn's moon Enceladus, which has been observed spewing geysers of water vapor into space, is considered one of the best places to search for microbial life within our solar system. The upcoming missions to these distant moons will be pivotal in our quest for understanding whether life exists elsewhere in the solar system. The Europa Clipper mission, set to launch in the 2020s, will provide detailed information about Europa's ice shell and the potential for a subsurface ocean. The Enceladus LifeFinder mission, still in the planning stages, aims to study the geysers of Enceladus in search of signs of life. These missions, along with others targeting Mars and Titan, could provide answers to some of the most profound questions in science. Does life exist elsewhere in our solar system? If so, what forms does it take, and what does it tell us about the possibilities for life elsewhere in the universe? Beyond our solar system, the search for exoplanets continues to be a major focus of cosmic discovery. The discovery of thousands of exoplanets over the past few decades has transformed our understanding of the universe and has opened up new possibilities for the existence of life beyond Earth. The next frontier in exoplanet discovery lies in finding Earth-like planets that are capable of supporting life. The James Webb Space Telescope, scheduled for launch in the near future, will be a game-changer in this regard. Webb's advanced infrared capabilities will allow scientists to study the atmospheres of exoplanets in unprecedented detail, looking for signs of habitability, such as the presence of water, oxygen, or methane. Webb's ability to observe distant exoplanets will revolutionize the field of astrobiology. Scientists hope to detect biosignatures, chemical markers that could indicate the presence of life, on exoplanets that orbit in the habitable zones of their stars. By studying these distant worlds, we may one day be able to answer the age-old question: are we alone in the universe? Webb is also poised to study the early universe, examining the first galaxies and stars that formed after the Big Bang, providing insights into the origins of galaxies, stars, and the elements necessary for life. In addition to the James Webb Space Telescope, other advanced observatories are being developed to probe the mysteries of the cosmos. The European Space Agency's Athena telescope, set to launch in the next decade, will study the universe in the X-ray spectrum, providing insights into the most extreme and energetic phenomena, such as black holes, neutron stars, and supernovae. The Square Kilometre Array, an international radio telescope project, will allow scientists to study the universe's earliest galaxies and the cosmic dawn, when the first stars began to shine. These and other next-generation observatories will deepen our understanding of the universe, shedding light on the origins of the cosmos and the complex processes that shape it. One of the most exciting frontiers in cosmic discovery is the exploration of black holes. For years, black holes were enigmatic objects that existed only in theoretical models, but recent advancements in technology have allowed us to observe them in ways never before possible. In 2019, the Event Horizon Telescope, EHT, captured the first-ever image of a black hole located in the center of the galaxy M87. This groundbreaking achievement has opened a new era in the study of black holes, allowing scientists to directly observe their event horizons and study the behavior of matter and energy in these extreme environments. As we continue to study black holes, scientists hope to uncover new insights into the nature of space-time, gravity, and the fundamental forces of nature. One of the biggest mysteries surrounding black holes is the information paradox, which asks whether information that falls into a black hole is lost forever. This paradox challenges our understanding of quantum mechanics and the nature of information in the universe. Solving this puzzle could provide crucial insights into the nature of reality itself, potentially leading to a unified theory that reconciles quantum mechanics and general relativity. Another exciting development in the future of cosmic discovery is the search for gravitational waves. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory, LIGO, made history by detecting the first-ever gravitational waves, ripples in space-time caused by the collision of two black holes. This discovery opened up a new window into the universe, allowing scientists to study cosmic events that were previously invisible to traditional telescopes. Gravitational waves provide a unique way to observe the most violent and energetic events in the universe, such as black hole mergers, neutron-star collisions, and the birth of supernovae. In the future, as more gravitational wave observatories come online, scientists will be able to study these cosmic events in greater detail, unlocking new insights into the dynamics of the universe. In the realm of theoretical physics, the future of cosmic discovery is just as exciting. Scientists are actively working on developing a theory of quantum gravity, a unified framework that can describe the behavior of both the very large, governed by general relativity, and the very small, governed by quantum mechanics. The search for such a theory could provide answers to some of the most fundamental questions about the universe, such as the true nature of black holes, the origin of the Big Bang, and the potential for time travel. String theory, loop quantum gravity, and other approaches are being explored as possible candidates for a unified theory of everything. Although a complete theory has yet to be found, the pursuit of this knowledge continues to drive much of the research in theoretical physics. As we look to the future of cosmic discovery, one of the most tantalizing possibilities is the search for extraterrestrial intelligence, SETI. Despite decades of searching, we have yet to find definitive evidence of intelligent alien civilizations. However, the rapid advancement of technology is opening up new avenues for the detection of technosignatures, signs of technological activity from distant civilizations. The discovery of extraterrestrial intelligence would be one of the most profound moments in human history, fundamentally changing our understanding of life, the universe, and our place within it. Whether we find signs of extraterrestrial life through radio signals, space probes, or other means, the search for intelligent alien civilizations remains one of the most exciting and ambitious goals of scientific exploration. While the quest to uncover the mysteries of the cosmos is vast and ever-expanding, one thing is certain: the future of cosmic discovery is incredibly bright. With advancements in technology, new missions, and groundbreaking theories, we are poised to make discoveries that will forever change our understanding of the universe. Each new mission, each new discovery, brings us one step closer to answering the deepest questions about existence. Are we alone in the universe? How did the universe begin? What is the fate of the cosmos? These are questions that have driven humanity's quest for knowledge for centuries, and the future promises to provide more answers than we ever thought possible. The discoveries of tomorrow may be even more surprising than those of today. As we continue to explore the universe, we will undoubtedly encounter mysteries that challenge our assumptions, push the boundaries of our knowledge, and redefine what we think is possible. The cosmos is vast, and its secrets are waiting to be uncovered. As we look to the stars, we are reminded that the journey of discovery is not just about finding answers. It's about embracing the unknown, seeking the truth, and continuing to push the boundaries of human knowledge. The future of cosmic discovery is a future filled with wonder, excitement, and infinite possibilities.